Saturn has always been a marvel of the solar system. With its stunning rings, mysterious atmosphere, and overwhelming size, it's no wonder that it continues to captivate scientists and skywatchers alike. But behind its beauty lies a complexity that challenges some of our most fundamental assumptions about how planetary systems work. The gas giant Saturn, the second largest planet in our solar system after Jupiter, is composed primarily of hydrogen and helium. It has no solid surface, only thick, swirling clouds stretching thousands of kilometers deep into its gaseous interior. Temperatures in its upper atmosphere hover around -113 degrees Celsius, while pressures deep below could crush anything sent there. But what truly makes Saturn stand out are its iconic rings. These rings are not solid, like a CD or vinyl disc. Instead, they're composed of billions of individual pieces of ice, dust, and rock. Some are as small as grains of sand, others as large as buses or small buildings, and they orbit Saturn at incredible speeds, forming thin, precise bands that can stretch for hundreds of thousands of kilometers, yet be only a few meters thick. This razor-thin structure is one of the great mysteries of planetary science. Why does Saturn have such spectacular rings, while Jupiter, Uranus, and Neptune, though they also have ring systems, have ones that are faint and barely visible? What keeps Saturn's rings from collapsing into the planet or dispersing into space? And more intriguingly, how old are these rings? For decades, scientists believed the rings were as old as the planet itself, over 4 billion years. But recent data from the Cassini spacecraft has shaken that assumption. Before it plunged into Saturn's atmosphere in 2017, Cassini spent years orbiting the planet, collecting high-resolution data about the rings. What it found shocked researchers. The rings may only be 100 to 200 million years old. If that's true, then they appeared well after the age of the dinosaurs. That raises an even deeper question. How did they form? One theory suggests that a large icy moon of Saturn was torn apart by tidal forces. As it drifted too close, Saturn's gravity shredded it into countless fragments, which then spread into a disk. Another idea is that cometary collisions may have bombarded Saturn's moons, scattering icy debris into orbit. Either way, the rings may be a temporary feature, destined to fade over the next few 100 million years as the material gradually rains down onto the planet. And yet, despite their impermanence, the rings influence Saturn in strange and unexpected ways. They interact gravitationally with Saturn's moons, shaping their orbits and even their geological activity. Enceladus, one of Saturn's icy moons, sprays plumes of water vapor and organic molecules from its south pole, possibly indicating a subsurface ocean. Some scientists believe that the rings help maintain this activity by influencing Enceladus's orbit, causing tidal heating in its interior. Even more fascinating is that the rings may affect Saturn's atmosphere itself. Observations have shown that the ring shadows can cool portions of the planet's upper atmosphere, creating seasonal weather patterns. In other words, the rings are not just ornaments, they are active participants in the system's complex dance. But Saturn isn't only about its rings. The planet's magnetic field is another puzzle. It's perfectly symmetrical, unlike Earth's or Jupiter's, which challenges our understanding of how magnetic fields are generated. The planet also has hexagonal storm patterns at its north pole, rotating with eerie precision year after year. And then there's Titan, Saturn's largest moon, bigger than the planet Mercury. Titan has a thick atmosphere, rivers and lakes of liquid methane, and possibly a subsurface ocean. It's one of the most Earth-like worlds we've ever encountered, despite being frigid and alien. Saturn, in all its grandeur, reminds us that beauty and mystery go hand in the cosmos. It's a world of paradoxes, majestic but deadly, simple in appearance but complex in nature. With every probe we send, and every image we capture, we uncover another layer of awe and another reason to keep exploring. At Infinity Beyond, we dive into these cosmic wonders not just to observe, but to understand. Saturn is not just a planet, it's a window into the forces that shaped our solar system and may govern worlds beyond. When you look up at Saturn, the first thing you might notice are its breathtaking rings. But orbiting quietly in its shadow is a moon that might just be more fascinating than the planet itself. That moon is Titan, and it holds the secrets to some of the greatest questions in planetary science. Titan is the largest moon of Saturn, even bigger than the planet Mercury. At a glance, Titan may not seem special. It's enveloped in a thick orange haze, and its surface is hidden beneath dense layers of atmosphere. But what lies beneath that veil is nothing short of extraordinary. Titan is the only moon in the solar system with a dense atmosphere, so dense, in fact, that it's over 50% thicker than Earth's. It's primarily made of nitrogen, with traces of methane and hydrogen. And what's even more bizarre, Titan has weather. Not just random gusts of wind or occasional storms, but a full-blown methane-based hydrological cycle. That's right, just as water evaporates, condenses, and rains down on Earth, methane does the same on Titan. There are clouds of methane, rain showers, and even rivers and lakes of liquid hydrocarbons flowing across its icy surface. Incredibly, these lakes gather in lowland basins, forming vast, shimmering seas, some of them larger than Lake Superior. The Cassini-Huygens mission, a joint endeavor between NASA and ESA, changed everything we knew about Titan. When the Huygens lander descended onto Titan in 2005, it became the first spacecraft to land on a body in the outer solar system. What it captured was breathtaking. A dry, cracked surface resembling a river delta, formed not by water, but by methane. And Cassini's orbital observations revealed sand dunes, shorelines, rain erosion, and even evidence of seasonal weather. These are Earth-like landscapes, but shaped by entirely alien chemistry. It's a frozen version of our own planet, operating on a completely different set of rules. What makes Titan even more intriguing is what lies beneath the surface. Strong evidence suggests that Titan harbors a vast underground ocean of liquid water mixed with ammonia. This subsurface sea may lie under dozens of kilometers of ice, but it has the potential to host microbial life. And here's where the real excitement begins. Titan presents two possible environments for life. One, the subsurface ocean, may mirror environments on Earth where life thrives around hydrothermal vents. The other, more speculative, involves the methane-rich lakes on the surface. Could there be exotic life forms that breathe hydrogen and metabolize methane? Scientists don't know yet, but Titan is a prime candidate for astrobiological exploration. Unlike Mars, where the search for life focuses on past potential, Titan may harbor life right now, either deep beneath its crust or floating in its hydrocarbon lakes. NASA is already planning its return. The Dragonfly mission, set to launch in the 2030s, will be a nuclear-powered drone that will fly across Titan's diverse terrain, analyzing surface composition and searching for prebiotic chemistry and biosignatures. It's a mission unlike any other, an autonomous flying laboratory on an alien moon. But Titan isn't just interesting because of life. It also mirrors early Earth in several ways. Scientists believe Titan today resembles what Earth may have looked like billions of years ago before life emerged. Studying its chemistry could provide key insights into the origins of life, not just here, but across the cosmos. And there's something poetic in that. A cold, distant world, shrouded in orange mist, may help us understand how life began on the warm blue dot we call home. Back on Saturn, the gravitational relationship between the planet and Titan creates tidal forces that help keep Titan's interior warm, despite its frigid environment. This same interaction could be driving geological activity and helping maintain the subsurface ocean. From the view of the Cassini spacecraft, Titan was not just a moon, it was a world, one with valleys and lakes, wind and rain, and the very real possibility of life. At Infinity Beyond, we believe that places like Titan aren't just destinations, they're keys to unlocking who we are, where we came from, and whether we are alone in the universe. With every discovery, we step closer to that truth. Titan invites us to imagine not just alien life, but alien landscapes, alien weather, and alien biochemistry. It's not science fiction, it's real, and it's only just beginning to reveal its secrets. Among Saturn's more than 140 moons, one stands out not for its size or beauty, but for what might lie beneath its frozen surface. That moon is Enceladus, a small, icy world only about 500 kilometers across, yet one of the most promising places in the solar system to search for alien life. At first glance, Enceladus looks like a featureless snowball, bright, reflective, and seemingly dead. But looks can be deceiving. Beneath that white exterior is a hidden ocean, and from cracks near its south pole, geysers of water vapor burst into space, revealing secrets from deep inside. These towering plumes, some stretching hundreds of kilometers into space, were first discovered by NASA's Cassini spacecraft. What Cassini found shocked the scientific world. The plumes were not just water vapor. They contained organic molecules, salts, and even tiny grains of silica, evidence of hydrothermal activity on the seafloor. In other words, Enceladus isn't just icy, it's active. Deep beneath its shell, there appears to be a global ocean of salty liquid water, heated by tidal forces as the moon flexes under Saturn's gravity. This heating may create environments similar to Earth's hydrothermal vents, where life thrives in total darkness, fueled not by sunlight, but by chemistry. This revelation is enormous. On Earth, hydrothermal vents are home to entire ecosystems, worms, bacteria, and exotic life forms that don't rely on the sun. Could Enceladus support similar forms of life? Microorganisms that evolved in complete isolation, in a completely alien ocean. The Cassini mission didn't just observe Enceladus from afar. It flew directly through its geysers. And during those flybys, it sampled the material in real time. It detected complex organic compounds, some with carbon chains that hinted at prebiotic chemistry. One of the most tantalizing finds was hydrogen gas, a key ingredient for microbial life. On Earth, hydrogen feeds methanogenic archaea, ancient organisms that live in extreme environments. If similar life exists on Enceladus, it would survive deep in the ocean, feeding on the chemistry between water and rock. And here's the stunning part. We don't even need to drill through the ice to study it. The plumes are natural vents, delivering samples straight into space. Future missions could simply fly through and collect fresh material, like drinking from a fountain of alien chemistry. This makes Enceladus a prime target for astrobiological exploration. Some scientists argue that it is the best place in the entire solar system to find life beyond Earth. NASA and ESA have proposed missions, some involving orbiters, others landers, and even robotic submarines that could one day explore the subsurface ocean directly. But even without landing, a new mission could detect biosignatures, molecules or patterns that strongly suggest the presence of life. Beyond its habitability, Enceladus is scientifically fascinating in other ways. Its geological activity is localized mostly to its south pole, where a region known as the Tiger Stripes splits the ice with deep fissures. These ridges, glowing faintly warm in infrared, are where the plumes erupt, powered by a subterranean ocean under pressure. Enceladus also helps feed Saturn's E-ring, one of the planet's faint outer rings. The icy particles ejected from its geysers are caught by Saturn's gravity, forming a glowing halo that stretches around the planet. It's a perfect example of how moons and rings are deeply interconnected. And while Enceladus is small, it punches far above its weight. Its reflective surface makes it one of the brightest objects in the solar system, reflecting over 90% of the sunlight that hits it. Its internal ocean, sustained heat, and geyser activity place it in a league of its own among icy worlds. In the cosmic quest for life, Enceladus represents a rare opportunity. It has liquid water, chemistry, heat, and energy, all the ingredients scientists believe are essential for life. Unlike Mars or Europa, where accessing the interior is difficult, Enceladus offers its secrets freely through its geysers. At infinity beyond, we believe that Enceladus is more than a moon. It's a message, a whisper from the cosmos that life may not be unique to Earth, that even in the coldest corners of our solar system, biology might emerge wherever the right ingredients come together. What would it mean if we found life here, on a moon no bigger than England, orbiting a distant gas giant? It would rewrite the story of life itself. It would prove that the universe is not a silent void, but a living, evolving ecosystem of worlds waiting to be discovered. So as we point our telescopes toward the stars and send our probes into the unknown, let us remember Enceladus, not just for its geysers or its ocean, but for its potential to answer the most profound question of all. Are we alone? Saturn is a planet of rings, moons, and mysteries. But beyond the spectacular visuals of its shimmering halo and icy satellites, there lies a deeper enigma, hidden within its swirling clouds and unseen forces. From a storm shaped like a perfect hexagon to a magnetic field that defies logic, Saturn continues to surprise scientists at every turn. Let's begin at the North Pole. If you were to fly above Saturn, through its golden haze, you would find something you'd never expect on a gas giant: a massive six-sided storm. This isn't an illusion or a trick of lighting, it's real. The hexagon storm is a jet stream over 30,000 kilometers wide, wider than two Earths placed side by side, rotating with eerie precision. Discovered by the Voyager missions in the 1980s and later studied in detail by the Cassini spacecraft, this storm system has baffled scientists for decades. Its six equal sides form a perfect geometric shape that remains stable over time. It doesn't wobble, it doesn't stretch or shift erratically. It spins around Saturn's North Pole at about 320 kilometers per hour, and has likely been doing so for hundreds, maybe thousands of years. So what causes this strange shape? Laboratory simulations suggest that hexagonal patterns can emerge when fluids rotate at different speeds, what physicists call differential rotation. Saturn's atmosphere is layered and dynamic, with powerful jet streams shearing across each other. But the stability and symmetry of the hexagon still puzzle researchers. Why six sides? Why does it persist? Why does it exist only at the North Pole and not the South? And it's not just a visual oddity. Inside the hexagon lies a giant storm, much like Jupiter's Great Red Spot, spiraling violently with a central eye. High above the hexagon, Saturn's auroras flicker in ultraviolet light, dancing to the rhythm of a magnetic symphony that scientists are still trying to decode. Which brings us to another of Saturn's mysteries: its magnetic field. All giant planets generate magnetic fields. Earth's is tilted and irregular. Jupiter's is massive and twisted. But Saturn's magnetic field is almost perfectly symmetrical with its rotation axis. This is incredibly strange. According to current scientific models, a magnetic field shouldn't be that symmetrical. Planetary magnetic fields are thought to be generated by dynamo action, a process involving the movement of electrically conductive fluids inside the planet. In Saturn's case, it's believed to be metallic hydrogen rotating deep beneath its clouds. But to create a perfectly symmetrical field, There would need to be an uncanny balance in this chaotic internal flow, something scientists don't fully understand. This symmetry makes it hard to measure Saturn's day length precisely. On Earth or Jupiter, we can track the magnetic field's rotation to determine how long a day is. But Saturn's magnetic field spins too smoothly. It's like trying to detect motion in a clock with no hands. Cassini attempted to solve this puzzle by using other clues, like changes in radio wave patterns and gravitational measurements. The current best estimate of a Saturnian day is about 10 hours and 33 minutes, but even that could be off by several minutes. That's a huge uncertainty for a planet we've studied for over 4 decades. The mystery deepens when we examine Saturn's interior. Unlike rocky planets, Saturn doesn't have a well-defined surface. Instead, it's made of layers of gas that gradually become denser with depth. Somewhere deep inside, hydrogen is compressed into a metallic state, where it can conduct electricity and sustain the magnetic dynamo. But how deep does this layer go? What's the structure of its core? Is it a dense rock or a diffused region of slushy metals and gases? One hypothesis suggests that Saturn may have a fuzzy core, a region not sharply separated from the rest of the planet, but rather blending gradually into its inner layers. This could explain why Saturn's magnetic field is so smooth and symmetrical. And yet, despite all this complexity, Saturn remains one of the most beautiful planets to observe. Its cloud layers swirl with subtle color variations, bands of beige, gold, and white, driven by powerful winds that can reach up to 1,800 kilometers per hour, the fastest in the solar system. Storms frequently rage across its equator, some of them so large that they can be seen from Earth through small telescopes. Every 30 Earth years or so, a great white storm erupts, an enormous lightning-filled superstorm that circles the planet and alters its atmosphere for years. What's truly astonishing is how interconnected all of these features are. The magnetic field affects the auroras, which are influenced by solar wind and Saturn's rotation. The storms affect cloud patterns, which in turn are shaped by jet streams and planetary rotation. Everything on Saturn, from the shape of its poles to the speed of its winds, is part of an elegant, yet still largely mysterious, system. At infinity beyond, we view Saturn not just as a planet, but as a puzzle. A celestial machine whose beauty is matched only by its complexity. A world that forces us to ask deeper questions about how planets form, evolve, and maintain their mysterious inner workings. And as technology advances, we may one day send probes deep into Saturn's atmosphere. We may peer through the clouds and hear the storms. We may even unlock the secrets of its magnetic heart. Until then, Saturn remains a giant enigma, wrapped in clouds, surrounded by rings, and governed by forces we are only beginning to understand. In the grand theater of the cosmos, Saturn isn't just a solo performer. It commands a gravitational ballet of over 140 known moons, each spinning and twirling in orbits that range from chaotic to perfectly timed. These moons do more than orbit passively. They interact with one another, influence Saturn's rings, and even affect the internal heat and structure of each other. This intricate system makes Saturn more than just a gas giant. It's the centerpiece of one of the most dynamic gravitational laboratories in the solar system. Let's begin with the most prominent members of this cosmic ensemble: Titan and Enceladus. Titan, with its dense atmosphere and methane lakes, and Enceladus, with its icy geysers and potential for life, are vastly different, but they are linked in subtle, powerful ways. Both moons experience gravitational tugs from Saturn and from each other. These repeated stretches and compressions are known as tidal forces, and they have enormous effects. Tidal heating is the main reason Enceladus maintains a liquid ocean beneath its icy crust. Without these forces, Enceladus might be completely frozen. And Titan? Its thick atmosphere and possibly warm interior may also be sustained in part by gravitational friction, keeping its methane cycle active and its surface dynamic. But it doesn't stop there. Moons such as Mimas, Tethys, Dione, Rhea, Hyperion, and Iapetus all contribute to Saturn's complex gravitational system. Many are locked into what's known as orbital resonance, a kind of cosmic rhythm where the moon's orbits are synchronized. For example, Mimas and Tethys are in a 2-to-1 resonance, meaning Mimas completes 2 orbits for every 1 orbit of Tethys. This kind of relationship helps stabilize orbits but can also amplify tidal forces over time. The result? Tectonic activity, geysers, or even internal oceans in worlds once thought geologically dead. Then there's Pan, a tiny moon shaped like a flying saucer, located in the Encke gap of Saturn's A-ring. It acts like a shepherd, keeping ring particles in line and carving out a clean path in the debris. Prometheus and Pandora, often referred to as the F-ring shepherds, perform a gravitational tug-of-war that keeps the narrow F-ring in check, twisting it, pulling it, shaping it like a rope in space. These moons are not passive. They're sculptors of the ring system. Their orbits affect the spacing, density, and movement of ring material. In turn, the rings also exert feedback, slightly adjusting the moon's orbits over time. What's more, some of Saturn's moons may be temporary. Evidence suggests that certain small moons could have formed recently, created by collisions of larger bodies or the gravitational collection of ring debris. This paints a picture of a living, evolving system, not frozen in time, but constantly changing. Take Iapetus, for example. It's a moon with a 2-tone surface, one side dark as coal, the other bright as snow. Its odd equatorial ridge makes it look like a walnut in space. No one's quite sure what caused the ridge. Perhaps ancient volcanic activity, or the remnants of a collapsed ring. Iapetus defies easy explanation. And then there's Hyperion, a sponge-like moon that tumbles chaotically as it orbits. Unlike most moons, which rotate in a predictable way, Hyperion tumbles unpredictably, a victim of irregular shape and gravitational kicks from Titan. It was the first non-spherical moon found to rotate chaotically, offering a stunning example of orbital physics in action. Beyond these well-known moons, Saturn hosts countless moonlets, some just a kilometer wide, hidden within the rings or orbiting in resonance clusters. As technology improves, we continue to discover more, each with a unique role in the planet's gravity-driven ballet. And the interactions don't just influence the moons. Saturn itself responds to the gravitational pull of its satellites. Its shape, rotation, and even internal vibrations are subtly affected. In fact, researchers recently detected ring waves, ripples in Saturn's rings caused by oscillations in the planet itself. These are like seismic readings, giving scientists insight into Saturn's core structure and internal density. In a very real sense, Saturn and its moons are co-evolving. Their fates are intertwined. The orbits of moons change over millions of years. Some may spiral outward and escape. Others may crash into the planet or be ripped apart to form new rings. It's a dynamic, ever-changing portrait of celestial physics. At Infinity Beyond, we're mesmerized by this dance, not just for its beauty, but for what it tells us about our universe. Studying Saturn's moon system offers clues about how planetary systems form, how gravitational forces shape evolution, and how life-supporting environments can emerge in the most unlikely places. So next time you see an image of Saturn, look closer. Beyond the rings, beyond the clouds, there's a ballet in progress, a celestial choreography billions of years in the making, still unfolding today. They're one of the most iconic sights in the universe. Saturn's rings, glittering like a cosmic halo in the blackness of space. For centuries, they've inspired wonder, imagination, and scientific debate. But as breathtaking as they are, Saturn's rings are also one of the solar system's greatest illusions. At first glance, the rings appear solid, smooth, thin disks gracefully wrapped around the planet. But when spacecraft like Cassini got up close, a different reality emerged. These rings are not solid at all. Instead, they're made up of billions of individual particles, each on its own orbit around Saturn. These particles range in size from tiny dust grains to massive boulders the size of houses. They're composed mostly of water ice, with traces of rock and organic material. The purity of the ice is what gives the rings their brilliant, reflective quality. Saturn's rings reflect up to 80% of sunlight, making them the brightest in the solar system. But their structure is even more astonishing. Saturn's rings stretch over 280,000 kilometers across, nearly 3/4 of the distance from Earth to the Moon, but they're incredibly thin, with most of them only 10 to 30 meters thick. That's like stretching a sheet of paper across the width of a football field. Their near two-dimensional nature is one of the most extreme physical contrasts in the cosmos. The rings are divided into several main sections: the A ring, B ring, and C ring, along with fainter features like the D, E, F, and G rings. Each section contains thousands of smaller ringlets, thin bands of particles that often weave in and out, driven by gravitational interactions with Saturn's moons. The Cassini division, a dark gap between the A and B rings, is a particularly fascinating feature. It's not truly empty, but contains fewer and smaller particles. The gap is caused by orbital resonances with the moon Mimas, which pulls ring particles out of that region with precise, repeating gravitational nudges. Beyond the dazzling symmetry lies a more sobering truth. Saturn's rings are temporary. For much of history, scientists believed the rings formed with the planet over 4.5 billion years ago. But new evidence from the Cassini grand finale suggests otherwise. As Cassini dove between Saturn and its rings in a series of death-defying maneuvers, it gathered precise data on the mass of the ring system. The results were shocking. The rings are much lighter than expected, only about 1/2,000th of the mass of the Moon. This, combined with erosion and gravitational decay models, suggests the rings are young, possibly only 100 to 200 million years old. In cosmic terms, that's a blink of an eye. If dinosaurs had telescopes, they might have witnessed the formation of Saturn's rings. So how did they form? One leading theory proposes that Saturn once had an icy moon that ventured too close. As it crossed the Roche limit, the distance at which a planet's gravity can tear apart a celestial body, the moon shattered, its remains slowly spreading into a ring. Another idea involves the collision of comets or asteroids with existing moons, flinging debris into Saturn's orbit. Whatever the origin, the rings are now gradually fading away. Micrometeorites and radiation are slowly darkening and degrading the icy particles. Saturn's gravity is also pulling material back toward the planet in a phenomenon scientists call ring rain. It's estimated that the rings could vanish in 100 to 300 million years, meaning we're incredibly lucky to witness them now. But Saturn's rings are more than a visual spectacle. They're a dynamic system, influenced by physics, resonance, and time. Waves ripple through them like sound through a vinyl record, caused by moonlets, gravitational pulls, and even Saturn's own seismic activity. Some ring sections show spiral density waves, similar to those in galaxies, offering scientists a unique laboratory to study gravitational dynamics. And the rings influence more than themselves. Their existence affects Saturn's atmosphere, its magnetic field, and even the orbits of its moons. The system is not isolated. It's a symphony where every instrument matters. At infinity beyond, we see Saturn's rings as a reminder of the universe's dual nature, eternal and ephemeral. They appear timeless, yet they are disappearing. They look solid, yet they are delicate and dispersed. They inspire wonder but also humility, reminding us that even the most majestic structures in space are transient. Imagine one day, far in the future, astronomers may look at Saturn and see only a bare planet, no rings, no glittering bands. The spectacle gone, only records and memories remaining. And yet, in this brief window of cosmic time, we are here. We are alive to witness Saturn's crown, and that is a privilege. Saturn dazzles us with its rings, storms, and moons, but some of its greatest mysteries lie deep beneath those swirling clouds. Unlike Earth or Mars, where landers can touch the surface, Saturn has no solid ground, no place to stand. Its outer layers are made of gas, transitioning gradually into dense, exotic fluids under crushing pressure. And far beneath all of that, a mysterious heart we still can't fully see. We call it Saturn's core, but what exactly is it? For decades, scientists believed that gas giants like Saturn must have formed around a solid core, a dense, rocky or icy seed that attracted gas from the early solar nebula. But recent findings, especially those from the Cassini mission, suggest a different story. Saturn may not have a well-defined, compact core. Instead, it might possess a fuzzy core, a massive, diffuse region where rock, ice, and metallic hydrogen slowly mix over thousands of kilometers. This fuzziness challenges how we think about planetary interiors. On Earth, we can detect earthquakes to understand our planet's structure. On Saturn, we rely on something much more subtle: ring seismology. As strange as it sounds, Saturn's rings act like a seismograph. When the planet vibrates, whether from internal oscillations or gravitational shifts, those movements create waves that ripple outward into its ring system. By studying the patterns and frequencies of these ripples, scientists can infer what's happening deep inside the planet. In 2019, using data from Cassini, researchers discovered ring waves caused by Saturn's internal oscillations. These readings hinted at a core much larger than expected, possibly stretching over 60% of the planet's radius. But instead of being dense and compact, it seemed to be diluted, spread out, and mixed with surrounding materials. This blurry boundary core, composed of rock, ice, and metal mingled with hydrogen and helium, defies traditional planetary models. It means Saturn isn't a planet with layers like a cake. It's more like a smoothie, blending materials that were once thought to be separate. But how did this structure form? Some theories suggest that during Saturn's early history, massive impacts or intense heat caused mixing between the core and the surrounding envelope. Others believe this is simply how giant planets form in low-density regions of the solar system. Regardless of the origin, it tells us something profound. Planet formation is far more complex than we imagined. Another fascinating question is, how much does Saturn weigh? It seems simple, but measuring a gas giant's exact mass distribution is incredibly challenging. Gravity mapping by Cassini helped provide new data, revealing how mass is distributed throughout the planet. This helped refine our understanding of the core and its composition. Saturn is about 95 times more massive than Earth, but it's also the least dense planet in the solar system. So light, in fact, that it would float in a giant bathtub, if one were big enough. This low density is part of the puzzle. It tells us that Saturn is mostly made of hydrogen and helium, but exactly how those elements behave under intense pressure and temperature, especially in metallic form, is still being studied in labs and simulations. Even more intriguing is Saturn's slow helium rain. Deep within the planet, helium separates from hydrogen and begins to condense into droplets, which then fall toward the core. This helium rain may release energy as it descends, possibly explaining why Saturn emits more heat than it receives from the Sun. In essence, Saturn is still glowing from within, powered not just by the leftover heat from its formation, but also by active internal processes. And yet, despite these breakthroughs, many questions remain. What exactly is Saturn's core made of? How did its internal structure evolve over time? Could its metallic hydrogen layer support exotic forms of matter or magnetism? What role does internal motion play in driving the planet's mysteriously symmetrical magnetic field? Answering these questions will require more than flybys. One day, we may send a probe deep into Saturn's atmosphere, equipped with pressure-resistant instruments that can descend far beyond what Cassini achieved. A future Saturn entry mission could send back real-time data from the heart of the planet, revealing a world we've only glimpsed from afar. At Infinity Beyond, we believe that understanding what lies inside Saturn is not just about planetary science. It's about knowing the building blocks of solar systems, the processes that shaped not only Saturn, but Jupiter, Uranus, Neptune, and even giant exoplanets orbiting distant stars. Because if Saturn has a fuzzy core, maybe those other worlds do too. Maybe the recipe for planets is more fluid, more dynamic, and more surprising than we ever dared imagine. And maybe, just maybe, the deeper we go into Saturn, the more we'll discover about our own cosmic origins. Before the Cassini mission, Saturn was a beautiful mystery, admired through telescopes, partially revealed by Voyager flybys, but still shrouded in clouds, ice, and shadow. That all changed in 2004, when a spacecraft named Cassini slipped into orbit around the ringed giant and began one of the most ambitious and successful explorations in human history. Launched in 1997, the Cassini-Huygens mission was a collaboration between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASI. After a 7-year journey through the solar system, including gravity-assist flybys of Venus, Earth, and Jupiter, Cassini finally arrived at Saturn, becoming the first spacecraft to orbit the planet. What followed was a 13-year odyssey that rewrote the science of Saturn. Cassini orbited the planet 294 times, flew by Titan 127 times, and made 23 close flybys of other moons, including Enceladus, Dione, Rhea, and Hyperion. It dove between the rings, sampled the planet's magnetic field, captured over 450,000 images, and sent back nearly 500,000 gigabytes of data. But Cassini wasn't just a camera in space. It was a floating laboratory carrying 12 scientific instruments that could peer through Titan's haze, map Saturn's magnetosphere, and even sniff the geysers of Enceladus. Let's talk about Titan. Before Cassini, we knew Titan had a thick atmosphere, but not much more. Cassini changed that forever. It deployed the Huygens probe, which in 2005 became the first spacecraft to land on a body in the outer solar system. The descent lasted over 2 hours, and the data it collected was revolutionary. Huygens revealed that Titan has rivers, lakes, and seas of liquid methane and ethane, flowing across a solid icy surface. It recorded pebbles made of water ice, clouds drifting above a hydrocarbon-rich sky, and a landscape eerily reminiscent of early Earth. Titan was no longer just Saturn's largest moon, it was a world. Then came Enceladus. Cassini's instruments detected plumes of water vapor and ice particles erupting from the south pole of this tiny moon. Later, flybys confirmed that the plumes contained salts, organics, and hydrogen gas, clues pointing to a subsurface ocean and possible hydrothermal activity. Cassini had uncovered one of the most promising places to search for alien life in our solar system. Cassini also gave us unprecedented views of Saturn's rings, revealing intricate structures, ringlets, waves, and mysterious propeller-shaped features caused by hidden moonlets. It showed how the moons interact with the rings, carving gaps, bending particles, and shaping edges like artists with gravitational brushes. But perhaps Cassini's most poetic moment came at the end. In 2017, running low on fuel and to prevent possible contamination of Titan or Enceladus, NASA chose to end the mission with a dramatic series of orbits called the Grand Finale. Over 22 daring dives, Cassini passed through the narrow space between Saturn and its innermost ring, something no spacecraft had ever attempted. During these final orbits, Cassini gathered crucial data about Saturn's gravity field, magnetic field, atmospheric composition, and the mass of its rings. And on September 15, 2017, Cassini made its final plunge into Saturn's atmosphere, sending data until the very last moment before it was torn apart. It was a heroic end to a heroic mission. Cassini's legacy goes beyond the numbers and discoveries. It taught us how dynamic, complex, and interconnected a planetary system can be. Saturn is not just a planet. It's a symphony of forces, rings that whisper of destruction and creation, moons that might host alien oceans, magnetic fields that defy symmetry, and atmospheres that glow with storms and secrets. Thanks to Cassini, we now understand Saturn not as a cold, distant gas giant, but as a living world, teeming with movement, chemistry, and potential. At Infinity Beyond, we honor the missions that push the boundaries of human knowledge. Cassini didn't just explore Saturn. It transformed it from a distant icon into a deeply studied world. It connected Earth to the outer solar system in a way nothing else had done before. And most importantly, it showed us what's possible when nations collaborate. Scientists dream big, and humanity reaches for the stars, not just with curiosity, but with courage. As we look forward to future missions like Dragonfly to Titan or potential orbiters for Enceladus, we stand on Cassini's shoulders. Its data will continue to yield discoveries for decades. Its images will continue to inspire generations. And its journey will remind us that even in the farthest reaches of our solar system, there is wonder waiting to be found. Saturn is more than a planet. It's a symbol of cosmic elegance, a world whose beauty is matched only by its depth of mystery. But beyond the storms, the moons, and the glittering rings lies something even more profound. Saturn's legacy, the lasting impact it has had on science, culture, and humanity's understanding of the universe. Let's begin with the science. Every mission to Saturn, whether flyby or orbital, has revealed something groundbreaking. From Cassini's historic discoveries to the precision of ring seismology, Saturn has provided scientists with a living laboratory to test and expand theories of planetary evolution, gravitational interaction, magnetism, and even biology. Its rings, once thought eternal, now reveal the fleeting nature of planetary adornments. They challenge our perception of time, reminding us that even something so magnificent can fade away in a cosmic blink. Its moons, from Titan's methane lakes to Enceladus's geysers, have forced us to expand the criteria for life. No longer do we look only for rocky planets in habitable zones. Thanks to Saturn, we now ask, could life exist in subsurface oceans? Could alien organisms breathe methane or metabolize hydrogen? Are we missing entire biospheres hidden under ice, clouds, or even in ring systems? Saturn's influence goes far beyond its orbit. It has reshaped planetary science itself. We now look at exoplanets, giant gas worlds orbiting other stars, and ask, do they have rings like Saturn? Moons with thick atmospheres? Tidal heating that supports alien oceans? Thanks to Saturn, we have a blueprint for what to look for. It has become a template for distant giants that we'll never visit in our lifetime, but that we may one day observe from afar with next-generation telescopes. But Saturn's legacy isn't just about science, it's also about imagination. For centuries, Saturn has captured the human mind. From Galileo's first confused sketch of ears on a blurry orb, to Van Gogh's celestial swirls, to modern digital art and film, Saturn has always stood for something greater: wonder, mystery, transcendence. Writers, filmmakers, musicians, and dreamers have all found inspiration in its rings. Saturn represents what's just beyond our reach, a place too beautiful to be real, yet proven to exist. And then there's what Saturn teaches us about ourselves. In studying Saturn, we're not just learning about another world, we're reflecting on Earth. The contrast is stark and humbling. On Earth, life thrives in every corner, yet we see that elsewhere in our solar system, liquid water is hidden beneath kilometers of ice. Atmospheres can be thick with methane. Moons can spray organics into space. And beautiful systems like Saturn's can be fragile, temporary, and changing. It reminds us that Earth is not the center of the universe. It's one world among billions, precious, yes, but not unique. And that realization is both terrifying and exhilarating. Because if Saturn, with its vast moons, chemical energy, and warmth from within, can come so close to supporting life, then maybe life is everywhere. Maybe biology is not a miracle, but a natural consequence of planetary evolution, given the right ingredients and time. And that changes everything. At Infinity Beyond, we believe Saturn represents a threshold, a point where science, philosophy, and awe converge. It challenges what we know, dares us to dream bigger, and invites us to keep asking questions. What's next after Saturn? Future missions like Dragonfly will return to Titan, this time not with a lander, but with a flying drone, capable of traveling across vast methane lakes and dunes to search for complex chemistry and maybe signs of pre-life. Proposed missions to Enceladus will analyze its plumes in greater detail, with instruments designed specifically to detect biosignatures, molecular evidence of living organisms. And one day, we may build orbital platforms around Saturn's moons, or even artificial satellites within the rings, to study these systems continuously. Each new mission will build upon Saturn's legacy, pushing our understanding further. But even if we stopped today, if humanity never visited Saturn again, its influence would remain. The images captured, the data gathered, and the questions raised will echo through generations of scientists and explorers. In the end, Saturn teaches us that the universe is not just beautiful, it's structured, evolving, and filled with possibility. It shows us that truth can be stranger than fiction, and that we are only just beginning to scratch the surface of what's out there. So the next time you look at Saturn in the night sky, perhaps through a telescope or in a photograph, know this: you are not just looking at a distant planet. You are looking at a story of cosmic architecture, of icy particles and hydrogen storms, of hidden oceans and ancient origins. You are seeing one chapter in the great book of the universe. And it's a chapter we helped write. And that is Saturn's greatest gift, to remind us not only where we are in space, but who we are and what we're capable of becoming. We've journeyed through storms and rings, through icy moons and glowing auroras, into Saturn's invisible interior and out beyond its magnetic borders. But as our time with the ringed giant draws to a close, one thing becomes clear. Exploring Saturn was never just about Saturn. It was about unlocking the deeper truths of our universe, how planets form, how moons evolve, how life might arise in the most unexpected places. And most of all, how curiosity can transform a distant dot in the sky into a world we know intimately. From the very first glimpse through Galileo's telescope to the final transmission of Cassini as it burned in Saturn's atmosphere, our relationship with this planet has been one of revelation, wonder, and relentless pursuit of the unknown. We've walked the frozen dunes of Titan in our imagination, felt the geysers of Enceladus erupting beneath us, Trace the rhythms of gravitational ballet between Saturn's many moons. We've watched storms swirl with impossible geometry, listened to the ghostly songs of magnetic fields, and marveled at the fragility of rings dancing on the edge of existence. Saturn, more than any other world in the outer solar system, has taught us to look deeper, beneath the surface, beyond the obvious, past the boundaries of what we thought we knew. But now it's time to look forward, because while Cassini's journey has ended, and while our robotic emissaries are momentarily silent, a new era is dawning. The upcoming Dragonfly mission to Titan is poised to fly across alien landscapes with drone wings, sampling organic chemistry, studying prebiotic molecules, and perhaps uncovering the raw ingredients of life. Concept missions like Orbilander for Enceladus aim to orbit and then land on the Geyser Moon, plunging directly into its icy mysteries with instruments designed to detect biosignatures, molecular whispers of possible life. Even beyond Saturn, the technologies, questions, and insights we've gained are shaping how we approach exoplanets, ice giants like Uranus and Neptune, and the search for habitable worlds light years away. Saturn, in a sense, was the classroom where we trained our minds for bigger challenges. It showed us that oceans can exist under ice, that chemistry doesn't need sunlight to stir, that alien doesn't always mean distant or dangerous. It can mean familiar, beautiful, and subtle. So, what does Saturn mean now? It means that we are capable of greatness when we look up, that a species once bound to the ground by gravity can send its thoughts and tools across 1 billion kilometers and land on a moon wrapped in methane. That science and poetry are not opposites, they are partners, because it took both logic and wonder to build the Cassini-Huygens mission. It took math and dreams to ride the rings, dive through the gaps, and fly between worlds. Saturn stands as a reminder that we are not spectators in this universe. We are participants, explorers, storytellers, scientists, poets, engineers, seekers. And while Saturn's rings may one day vanish, while its moons may drift and its storms subside, the story we wrote there will remain, etched into data archives, scientific papers, images on classroom walls, and memories in the human spirit. At Infinity Beyond, we don't just report on science, we live by its fire. We carry it into the unknown, asking better questions, dreaming bolder dreams, and sharing the universe not as something out there, but as something we belong to. Because that's what Saturn has ultimately given us, a sense of belonging to something vast. A reminder that even though we are small, we are capable of reaching across darkness and distance, and finding beauty, order, and meaning. So as we close this chapter on Saturn, we open another. The cosmos still beckons. There are oceans to find, stars to measure, life, perhaps, to meet. And as long as we dare to look up, to wonder, to explore, the spirit of Saturn will live on. Not just in rings of ice or storms of hydrogen, but in us, in every question we ask, in every mission we launch, in every child who looks through a telescope and says, "What's that?" and dares to find the answer.